Hello all. This is review number 8, as you can see, and it was all of our parametric and vectors. So we'll just start with a couple of these first ones. These first 1 through 6 we've talked about. These aren't necessarily exactly the types of questions you will see on the AP test, but it gives us a little review of what a parametric equation is, or a vector, and what those are: just an x position and a y position that are defined by a third variable called our parameter. Usually for what we're doing, it's a t, because we're talking about our x position, y position at a particular time. So what this question is asking, state the type of figure that would result from the following parametric equations if they were graphed. If you didn't have a calculator, we would then graph them, direction of motion, and then write the Cartesian equation for that. I shouldn't say line here. It's just whatever the figure is. Some of these are lines, but not all of them. So with this one, what we did to identify sort of what this was, if it wasn't an obvious one, like some of the trig ones are here in a second, is we set up a little TXY chart. Here's our T's that we would use. And then we would just use these equations to identify what our X and Y positions were. Although now that I look at this, let's change this to a 0 so that we can do the square root of 0 to get a 0. And then in this case, if T is 0, Y is also 0. If we do a 1, we would get 1, 1. If we get 2, we would get what? Root 2, 2. And then the last one, we would get root 3, 3. So if we plotted those, here's 0, 0. If I then plotted the point 1, 1, and then let's do 2, 3, knowing that root 2 is a little bit bigger than root 1. It's like 1.4, 1.5, and then that's up here. And then root 3 will be a little bit bigger than 2. So, no, it isn't. A little less than 2. And then we're up here at 3. All right, so that's our graph. What you'll kind of see, and we'll verify this here in a second, is it's kind of a half of a parabola. The way we can get that half parabola, just to confirm, is just a little substitution here. If y equals t, then instead of doing x equals root t, which is what that first equation says, since t is equivalent to y, we can do a just simple little substitution there. Square both sides. So then when you get the radical to drop out, you get y equals x squared. So that's our Cartesian equation. This is the graph. What else did I want you to do? Direction. Since this was the time of 0, this was the time of 1, 2, 3. We were moving in this direction. And then the Cartesian, yeah, that's everything. All right. So the way we are going to be able to tell these is, if you notice, this has a degree of 1/2 and this has a degree of 1. So since that degree is half of the other, same with a parabola, a y to the first and an x squared, that's going to give you the parabola. Looking at number 2, since these degrees are the same, they're both 1s, not only just the same, but also 1, that then is going to tell us that this is going to be a line, or a segment, I should say, because we have a defined starting and ending point. If we know that it's a line segment, then when we set up our little TXY chart, we really can just start at the beginning of this time and end at that, and then just connect them in a line. So if we take that -2, plug that in, yeah, -2, so we get -4, so -9 is our x. A -2 here would be -15 overall. So let's plot this. So -9 we'll say is here. -15 we'll say is here. Remember, this is our first point. If I throw in 3, we get 1, 5. So 1, 5. This is our second point. We know it's a line segment. Those are really then the only 2 points we need. That's your direction. If I then want to write the equation, this one requires a little bit more work. But what I'm going to do is solve for t right here. I don't have a lot of room. So let's add the 5 over Then you'll divide by the 2, like so. And then we take that, plug it in for our y in this one. So we would do 4 times x plus 5 over 2, and then we still have the minus 7 here. This would cancel, reduces this down to a 2. Let's now distribute. So we would get 2x plus 10 minus a 7. And then y would equal 2x plus 3. Now that I look at my line here, I'm going to put this right on the y-axis. So this should be 5 up here at 1. And then that would make a little more sense that we have a slope of 2, and then that we would cross the y-axis at 3. Okay. And then the last types are the circles and the ellipses. So one of the big picture ideas that we want to keep in mind here, and then we don't necessarily have to do all of them, is if I do, let's do this one first actually. One where x is paired with cosine and y is going to be paired with sine, then it's going to behave just like our unit circle. So if we look at this one with coefficients of 1, this really would trace out the unit circle, radius of 1 going in a counterclockwise direction. But if we look at our domain for our time, we're going to start at pi over 2. And over here is negative pi, negative 3 pi over 2, and then 2 pi, not negative pi. But 1, negative 1, negative 1, 1. So we start at pi over 2 in the counterclockwise direction. This should give us 3/4 of a circle with a radius of 1. The way we get that is the identity, cosine squared of t plus sine squared of t equals 1. Here cosine is an x, so it's really just x squared. There the sine is a y, so that's a y squared. And then that's how we get that Cartesian equation of a circle with a radius of 1. If we did it here, gonna be similar in the sense that it's going to be a unit circle. You're going to get the entire unit circle, but it's going to go in the counterclockwise direction, and it's going to start and end differently than what this one would have started. So if we go up to 3, notice now how 3, let me create a little space here with this one. 3 and 4 look pretty similar. So we have x equals 2 sine, x equals 2 cosine, y is 5 cosine, here it's 5 sine, this is 0 to pi, this is 0 to 2 pi. So these are both going to be ellipses that stretch horizontally to negative 2, up 5, down negative 5. This one would go in a counterclockwise direction, and it's going to go, or it's going to start and end a little differently than what this one was. So this is going to be a half, but just be really careful, because now that these are flipped, we don't necessarily start over here at angle 0. So that's going to show what I mean. So if I let the time be a 0, I get the sine of 0, which is 0. If I let our t be a 0 here, I get the cosine of 0, which is 1 times a 5. So we actually start this one up here. If I go pi over 2, the y coordinate at pi over 2 is 1, and then we're going to double that, so 2. And then the cosine of pi over 2, so the x coordinate up there is a 0. Then we get to this point, and we went in this direction. If I go to pi then, the sine value, the y coordinate at pi is the 0 now. And then this should give you a negative 5 when you take your pi, plug it in here. So we do get our half ellipse like we're supposed to, but it's not the 0 to pi that we would be thinking if we did the unit circle. Where if it was this one, actually let's do this one. Let's stop this one at 0 to pi, because then it's still a half of an ellipse, but it's going to behave like the unit circle. We really don't have to think much about it. Oops, wrong direction. It's going to go in the counterclockwise direction. You can set up your little TXY chart if you want to confirm it. But now that x is with cosine, y is with sine, it's going to start at angle 0, then it's going to go to pi over 2, and that pi is going to go in the direction that you would think it would be going in. So still half ellipses, stretch horizontally and vertically the same, but we're just going to get a different half. And again, that's only if I change this, which I think might be a good idea, just so we can kind of compare them and see how they're similar yet different. And then the last part, how do we get our Cartesian equation? Same identity as the one below that we did, that sine squared of t plus cosine squared of t equals 1. It's just this time if I need this as a cosine, solve this for cosine, I would divide that 2 over. So cosine of t is really an x over 2 squared. If I solve this one for y, I would get y over 5. Solve it for sine. So sine is y over 5 squared, and then that equals 1. And then that's the equation of an ellipse. So those are our parametrics. 6, you can kind of look at that. It's going to be a circle. That'll give you the entire circle. 0 to pi is going to go in the direction of the unit circle. All right, now we start getting into more the types that you would probably want to make sure you could do. Finding the slope of a parametric, that's assuredly going to be on there. And it's the whole slope is change in y over change in x. Parametrically, what that would mean is our dy dt, so the derivative of the y with respect to time and the derivative of the x equation with respect to time. Divide those, that gives you the ratio that we want. So this one here, if I did the derivative of x, we would get dx dt, since it's in terms of time, and we would just get secant t tangent t. If I did the derivative of the y, so the change in y with respect to time, the variable on the other side, we would get secant squared of t. So if I want dy dt, we would need to take dy dt, divide it by dx dt. When that happens, the dt's cancel, giving us our dy dx. Because of that, we take what these are actually equivalent to. So the dy dt was this guy here. And then this dx dt was this one here. I'd probably clean that up a little bit. The secants will reduce, giving us one secant on top, tangent on the bottom. And then we need to evaluate that at pi over 4. All right. Denominator, let's do that first as the easy one. So tangent of pi over 4 is the 1, the root 2 over 2 divided by root 2 over 2. And then the secant is the reciprocal of cosine of pi over 4. So that's 1 over root 2 over 2, the reciprocal of root 2 over 2. So that really just gives us a 2 over root 2. Free response question-wise, totally acceptable. Multiple choice, they probably make you rationalize this. So multiply by root 2's over 2. Cancels, and our answer is then root 2. All right. A length of a parametric curve. Certainly we'll get this in some capacity. A lot of times it's used down here in these vectors. But if you are given that, it's just the integral of the square root. The reason for this is the Pythagorean theorem. When we prove this, the square root of dx dt squared plus dy dt squared. So if I want the length of that parametric curve here, I want to give you 10 seconds. It would be the square root of dx dt and then dy dt, each of those squared. So dx dt is the derivative of this guy. Pretty simple, 3t squared. Ran out of room over there. So dy dt is the derivative of this one, which would be the 2's cancel on the derivative, so just 3t. So we do 3t squared squared, and then dy dt is 3t squared. You throw it in the calculator, get your answer, but just be careful with the squareds. Make sure that we don't forget those, like I just did. Or no, I didn't. Because this here, 3t squared, the derivative of this, let me rewrite that just to make sure I'm not screwing that up. Yeah, 6t over 2, yeah. And then this is the derivative of the second one, and then square it. All right, now the rest of this is really, they'll construct a whole free response questions around these next handful of things. So these are pretty critical. We did a number of them in class. We're going to do a few more here in a minute. But it's all these different values. I'm going to have you add one also real quick. Let me make sure I didn't put it anywhere else. Yeah, so let's put in a distance here as well. So when we want the distance of these, if you recall, the speed of a vector is the magnitude of the vector or the length of that vector. And then the distance is us integrating that. So distance is going to look like that previous question. Since we're going to be finding the magnitude of our velocity vector, we integrate our speed. It's the dx dt squared over your dy dt squared. That's our distance. All right, again, that's nothing more than the magnitude of our velocity vector. That's why we're using our first derivatives, because the first derivative of your vector is your velocity vector. And then basically the second derivative of our vector is our acceleration vector. So we come down here, given the position vector of the particle at time t, to find the particle's velocity and acceleration and the speed. So pretty straightforward. If this is our velocity vector, here we're using these little carets, is nothing more than our first derivative. So negative 2 sine of t is the derivative of the first one. 3 cosine of t is the derivative of the second one. But then we want to find our velocity vector at pi over 2. So plug in pi over 2 for each of these. The y coordinate at pi over 2 is a 1, so this would become a negative 2. The x coordinate at pi over 2 is a 0, so that's our velocity vector at that time. We also want the acceleration vector, so take one more derivative. Should get a negative 2 cosine of t, and then a negative 3 sine of t. And then we want to evaluate that at pi over 2. The x coordinate at the time of pi over 2 is the 0. The y coordinate at the time of pi over 2 is the 1, so it's become a negative 3. That's our acceleration vector. Sorry, I'm up early on a Sunday morning with my dog, and every little thing he hears outside he's barking at right now. All right, then we need our speed. The speed is the magnitude of our velocity vector at the time that I'm asking you to identify, which in this case is pi over 2. So the magnitude of a velocity vector is really just the length of that velocity vector. Suppose I can write that in up here, so then you have it. All right, so like I said, here's the distance formula. Solved for, and the distance formula is really the Pythagorean theorem solved for the hypotenuse. And we're doing the distance formula, though, with our velocity vector. That's what we're doing with our first derivatives. So with this one, let me do this underneath so I don't go too far into number 10. Here's our velocity vector at that time, right? So we're going to take the negative 2 squared and then add that to, because again, all I'm doing now is taking what we found over here, but now we want the length of that. So we're going to take the negative 2 and square it. We're going to take the 0 right here and square it. That's the magnitude of our velocity vector. We end up with a root 4, and then our speed ends up being a 2. All right. So 10, pretty similar with number 10. Really simple little derivatives there. I'm not necessarily going to go through that. I'll try to post the key to this. I know a few of you have asked for the keys on previous ones that I haven't done all the problems with, but pretty much the same setup. This is an even easier version of this because those derivatives are so easy. We'll do another one with number 11, where it's a little harder, a little more interesting derivatives that we want to make sure we're squared away on. So for the first one, if I want the velocity vector at any time, it's the derivative of this. So we drop down the 2. The derivative of a natural log is 1 over the inside times the derivative of the inside, which would be a -3. The derivative of e should repeat itself, and then the derivative of your exponent. Let's clean that up a little bit. I may just cheat. So I have a little bit of room here, so I have enough space to do all this. So let's multiply those together. So that's just going to give me -6 over 1 minus 3t. So let me erase all that. So -6 over 1 minus 3t. And then now we're going to actually evaluate our velocity at the time of 1. So we would get a -6 over, if this is a 1, we get 1 minus 3, so -2. And then this would just become e to the 3 times a 1, so just 3e cubed. So then final answer for this vector, my velocity vector at the time of 1 is a +3, and then 3e to the 3 cubed. If I want the acceleration vector, we need one more derivative. So now we look at this, a little trickier. We now need to take the derivative of this thing. I'm going to guess most of us would do the quotient rule if we were to see this. So let's do the quotient rule with this. What's our denominator? 1 minus 3t multiplied by the derivative of the top, which would just be a 0, minus the top over your denominator. No. Time out 1 minute. Got a little anxious there to divide. So minus the top times the derivative of your denominator, which is a -3. And then we'll divide by your denominator squared. The derivative of this, we would drop our 3, and then the derivative of the e to the 3t should repeat itself, and then once again times the derivative of that exponent. So definitely probably want to clean this up a little bit. This cancels because of that 3. We end up with, what, a -18 overall for that numerator, and then over 1 minus 3t squared. And then this guy, 9e to the 3t. All right, while you write that, I'm going to just make sure I didn't screw that up. Yeah, looks good. And then you're going to evaluate that at 1. So we'll get a -18. Throw a 1 in here, so you're going to get a -2 squared. A 1 here would just be 9e cubed. So acceleration vector at the time of 1 is a -9/2, 9e cubed. Squeeze the speed in down here. So speed is, again, the magnitude or length of our velocity vector, in this case at the time of 1. If we go back up here, we have already found that in this problem. This was our velocity vector at the time of 1. So now we want the magnitude of that vector. So we would just do the 3 squared plus the 3e to the 3 squared. For response-wise, that's your answer. You can just leave that. If it's a decimal, then we're just evaluating that on our calculator. Okay. Then we did, so those are derivative ideas. If I give you a position vector, be able to take our first derivative, second derivative, velocity, acceleration. Then we did the antiderivative of these. So what this is telling us is this is your velocity vector. This is dr dt, and it's just a -1, -1. And then our initial position, so at the time of 0, we have an x position of 1 and a y position of 2. All right, so when it says the velocity of a particle and its initial position are given below, find the position of that particle. So the way we did this is we took this and we found the antiderivative. So the antiderivative dr dt would be r of t. The antiderivative of a -1 with respect to time would just be a -t plus your constant. So that's our x position currently. And then our y position would be the exact same thing. The antiderivative of -1 would be -t plus c. And then that's our y position. So then I actually had you write this. X of t is really this -t plus c. This is your y of t. So y of t, also a -t plus c. To figure out what the c's are, we're going to, at the time of 0, we know if I let this time here be a 0, that our x position is a 1. And then quickly we see that our c is going to be a 1 for our x position. So we can then go ahead, get ready to write our entire position, because what I've just found is in this x position right here, that c ended up being a 1. So we would do a -t plus 1. Now I know that's my x position for any time I want it. For the second one, if we let our time be a 0, then we can see that our y position was this 2. And then we now know that this, instead of a -t plus c, we just found that c to be a 2. We write -t plus a 2. That then is our y position at any time. This overall then is our position vector. It tells us where we're at anytime we want, x and y. 13 is just kind of the next step up from there. If I give you the acceleration vector, we're just going to have to do this a few times now. So if I did the antiderivative of the acceleration vector, that would then take me to my velocity vector. I'm going to write it as such. So we'll stop the dr dt. You could write it as dr dt though. All right, so either one. All right, then we're going to go through finding our antiderivative of these. So the way I would kind of approach this is the antiderivative of 0 would be a 0 plus c. So for those, let's go ahead and do 0t plus c, but it's still going to be a 0. And then this guy should give us a -32t plus c. From there, what this has now given us is that at the time of 0, so here's our dr dt, our rate of change with respect to our x was an 8. So that's what this one is. So we would say x primed is equal to 0t plus ac. Since this is 0 either way, like the time is 0 and we had a 0 for the coefficient, then our c would just end up being the 8. So we can then go ahead, get ready to write our velocity vector. This really just ends up being an 8. Wouldn't the exact same thing happen with this one? This just ends up being our initial y rate of change. This would have been y primed equals 0t plus c, but that's going to be an 8 as well. This one, again, you won't have to deal with 3 dimensions on the AP test. That's our z if we were moving in 3 dimensions. So let's say not only moving left and right, up and down, but away or towards us. This would be a -32t plus that c. And then we now know at the time of 0, that rate of change is 0. So that one actually then, if this is a 0 or c is a 0, we find that, in this case, our c is a 0. So a bunch of constants for our velocity. Do one more. Now we will call this r of t. So this would be 8t plus c, comma, and then we get another 8t plus c, comma, and then a negative 32t plus c. Then we need to find out what those c's are. So if you think at the time of 0, our x position is 0. Just because I'm running out of room, let me try to squeeze this in down here. Sorry, it's hard to keep things small with this pen on a computer. Get this to change. There we go. That this is 8t plus c. This is our x position. And what you're going to see is up here, our x position is 0 at the time of 0. So that c just ends up being a 0 right here. So our x position at any time is just 8t. This one would have been our y. That equals 8t plus c as well. So if we come up here, our time is 0, our y position is 0 at that time. So if we come down here, let our y be a 0. When our time is 0, that whole thing would just 0 out. That means that c here is also a 0, which means we're just going to get an 8t for that one as well. And then the last one, we do have a little something now, is this z position, negative 32t plus our constant. If we let our time be a 0 here, notice how our z position is 100. So let our z position be 100. At the time of 0, this is all 0, you'll see that your c in this one right here should be a 100. So that gives us negative 32t plus a 100, and then that's our position vector at any time. They will not probably have you do that 2 times, pretty messy, but that's how you would handle it. It's a good review of some old ideas anyway. All right, the rest of these then are old AP questions. So let's see how we can think these through. So if you want to take a minute, a lot of times if we're together at night, I would now give you a minute or two to try 14, see if we can kind of get through all of these. If you now look, all of these are just old questions that I pulled from old tests, and then we're going to have a few free responses in a second. So if you want to try it on your own, feel free. This one says the acceleration of a vector moving the xy plane is given by this. So again, that's our acceleration vector. And then they're giving you at the time of 0, our velocity vector would be 1, 0. And then they're asking you how fast it's going. So ultimately, at the time of 2, what they're looking for is our speed at the time of 2, right? So how fast are we going at 2? So the way we would evaluate that, we would want the magnitude of our velocity vector at the time of 2. That's the answer to this question. We first need to get our velocity vector because all they gave us is our acceleration vector, and then evaluate it at 2, and then we go ahead and find our speed. So if our acceleration vector is right now this negative pi sine of pi t, comma, and then 2t plus 1, then we need to do our antiderivative of this. So we take the antiderivative, let's consider this a negative sign. So let's drop the pi first. And then the antiderivative of a negative sign would be a positive cosine of pi t. And then if we have this here where our coefficient of the composite is a 1, we then have to divide by pi. So divide by this guy right here. These pi's will cancel, and then we get our plus c for that. Antiderivative of 2t plus 1 would give us a t squared plus a t plus our constant for our y position. Let me erase these just so there's a little less congestion. It won't take up too much room for me to work. So this is our x primed. And then this is our y primed. So it's our horizontal rate of change, vertical rate of change. And then what we are told, so I'm using this information right here, all right, because that's our velocity vector. At the time of 0, our horizontal rate of change was 1. So we would do the cosine of, let this time be a 0. So pi times 0 is 0 overall. And then our horizontal rate of change is a 1. So cosine of 0 is a 1 equals 1. So if I solve this for c, this c just ends up being a 0. If we move over to this one, again, let our time be a 0. So 0 plus 0. Our horizontal rate of change, y primed here, also a 0. So nicely, both of these c's just end up being a 0. So this is our velocity vector at any time. And what we have just found is that both of those c's are going to be a 0. So I'm going to come up here. Let's erase this c. Let's erase this c. And then now this is our velocity vector anytime that we want it. I suppose I could have erased the plus signs also. What we're now going to do is evaluate this at the time of 2. So my velocity vector at the time of 2, notice how we have the cosine of pi t, so that would become the cosine of 2 pi, comma, and then we plug in a 2 right here, we would get 4 plus 2, 2 squared, it's a 6. That's our velocity vector at that time. Let's go ahead and do cosine of pi, or 2 pi. 2 pi is same as 0, cosine of 0 is a 1. 6. So now that's our velocity vector at that time. Now we ultimately want the speed over here. That's the magnitude of that vector. So 1 squared plus 6 squared. 1 plus 36 is 37. Should get C for that answer. A lot of stuff going on there. So they're really testing you on 2 different ideas in one. All right, certainly something that we want to be able to do and expect to be able to do. All right, 15. Particle moves in the xy plane along the path of, and then you're given the curve y equals x sine of x. When the particle is at the point 3, and then comma 3 sine 3, the dy dt value is a -2. What is the value of dx dt at that same point? So think about what they're asking. Again, if you want to think this through on your own before I walk through this, go ahead and see if you can figure it out. We want to figure out what dx dt is, but we're not really given an x equation in terms of time. So ideally, what that would mean is if we kind of have x equals like the ones we did on the very first page, cosine of t, then the derivative of this we would say is dx dt equals a negative sine of t. But we're not given that. So we need to come up with that somehow. So what this one is getting, it's moving along this right here. The particle is at this position. Notice how we do have a dy dt. So if we want to use that at some point, we want to come up with a dy dt value. So what this is getting at, the way this is kind of hinting that we're working with, think about what dy dx is. Isn't dy dx dy dt divided by a dx dt? Look at the equation that they're giving you. So y equals x sine of x. So if I want dy dx, that's our product rule right here. So the derivative of x is a 1, leave the sine of x. And then leave the x alone. The derivative of sine is cosine. And then that's our dy dx. Well, what dy dx is equivalent to, if we're talking parametrically, is your dy dt divided by your dx dt. So I'm going to substitute that in here. So instead of saying dy dx equals the right-hand side, I'm going to say that dy dt over dx dt is equal to this sine of x plus x cosine of x. So what we've now created is what we're ultimately looking for, dx dt, right? And if you look at your dy dt here, don't we know what dy dt is at the time we're concerned about? It's a -2. So what I'm going to do is I'm going to replace the dy dt with a -2. Now we have an equation that we can solve for dx dt. So let's multiply the dx dt to the other side. So we'd multiply this over, and then we would have divided that sine of x plus x cosine of t over, so that we would get a -2 divided by all of that. So x plus x cosine of x. All right. Okay, hold on just a second. I need to pause this. One moment. All right, so then from there, all right, I wanted to set up my calculator, and it takes forever to get going and open, so it's ready to go. But now from here, this is the answer to our question, right? This is dx dt. This is what I want to figure out. So all I now need to do is evaluate this over here, but we're missing one little piece of information, but it's not hard to find, and that is what x is. So we just now need to plug in what our x is. Well, the piece of information we haven't used yet is this 3 sine of 3. So you just had to kind of think through what that means our x would be. So here's the equation that we were given to work with, right? That we took the derivative of to get our dy dx. Well, if x is 3 here, wouldn't that then give us a y coordinate of 3 sine of 3? So what that's telling you is if we're at this point, our x was a 3. So what we're simply doing now is evaluating this on the calculator. Let x be a 3 for all of this. So I'm going to do -2 over sine 3 plus 3 cosine of 3. I have that now plugged in here, you can see. And then you'll notice that that's going to give you that 0.70, round that third decimal to 7. And then this is your answer. All right, this one won't need our calculator here. These look like nice answers that we want to do without calculator. Particle moves in the xy plane, so the velocity vector for any time is given by, you're given the velocity vector. Particle has a position of 3, 0 at the time of 0. Find the position vector at the time of 1. So they're going to make us go backwards. This is our velocity vector. So if I want my position vector, let's call this r of t. The antiderivative of this, hopefully we recognize, these parentheses since that's what they used, is the inverse tangent of t plus our constant. The antiderivative of this is the exponential function. It repeats itself. And then we've got to divide by the natural log of 2 and then plus your constant. If I ultimately want my position vector at the time of 1, I need to find my position vector at any time. So that would mean we need to figure out what these c's are first. That's what this information was given to you for. So this again is x. And what we know is at the time of 0, our x position was a 3. The inverse tangent of 0 is 0, so that c is a 3. This is your y of t. So that's 2 to the t over the natural log of 2 plus your constant. And using this information up here, we know our y position is 0 at the time of 0. So this 2 to the 0 actually gives you a 1 over ln of 2. So when we subtract that over, this c is a negative 1 over the natural log of 2. So we can now go ahead and write our position equation. We're going to take this guy here, this inverse tangent of t, and we found that c to be a 3. And then we're going to take our y position, so 2t, or 2 raised to the t, over the natural log of t, minus the 1 over ln of t, certainly, or 2. You can certainly write that as one fraction. And we then now want to ultimately evaluate this position at the time of 1. So we get the inverse tangent of 1, whatever that is. We're going to add 3 to it. Let's go ahead and write this as one fraction now. So if this is a 1, wouldn't this just be a 2 minus a 1, giving us a 1 over that ln of 2? We see plenty of those up there with that 1 over ln of 2. And then we just have to evaluate this. The inverse tangent of 1 should be pi over 4. This is just asking you what angle. And again, first quadrant works with all these inverse tangents, so we're always kind of looking for that first quadrant angle first. And there is a first quadrant angle whose y divided by x is a 1, that's pi over 4. So we get, what letter is that? E. All right, 17, particle moves in the xy plane anytime greater than 0 according to these parametric equations. They're giving you your x position. They're giving you the y position. Which of the following statements about the particle are true? So it says the particle is moving to the right at the time of 1. I like this question because it really gets at the heart of what all these parametric ideas are giving you. So if we're just moving to the right, this here is the one that gives us horizontal motion. So if I'm going to determine if the particle is moving to the right at the time of t equals 1, I'm going to use this equation. I'm going to take its derivative, because if our derivative is positive at 1, that means our position is increasing. So that means left or right, we're moving to the right. If the derivative of our horizontal position is negative, that means our position is decreasing, means we are moving to the left. So x primed, evaluate that at the time we're asked about in this one, which is 1. So I would just get e to the 1. You wouldn't have a calculator in your hand, so they would expect you to know that e is about 2.7. So this is definitely greater than 0. It's positive, basically. So that means my x position is increasing. X position increasing means we are, in fact, moving to the right. So number 1 is true. So we can get rid of A, we can get rid of D, and we now know it's B, C, or E. If we're moving upwards, that's our vertical position only. So what that would mean is we're going to take our Y position, and if we're moving upwards, that means our Y position is increasing. So that would have to mean our derivative of Y, so 3 halves t to the 1 half minus a 2. That would have to be positive at the time of 4. So if we now evaluate it at 4, what we would have is 3 halves. Understand this is the square root, so square root of 4, and then minus a 2. These should cancel, and notice how this ultimately has a value of 1. So since y primed of 4 is also positive, in this case positive 1, that means our vertical position is increasing, making this statement also true. So we can now get rid of this one, and it's either 1 and 2 only, or all 3 of them end up being true. So now our third one. If the particle is at rest at the time of 0. So here's what's important about this question when it's parametric. At rest means you cannot have a vertical rate of change or a horizontal rate of change. So we need to test that both of these, the x rate of change and the y rate of change, is 0 at the time of 0. So we already have both. So let's take this x primed and evaluate it at 0. Notice how we're going to get 1 minus a 1. So this means we do not have a horizontal rate of change. So that's currently looks like maybe we are at rest, but that doesn't mean we aren't moving vertically. So we now want to take our y rate of change, which we hit over here, and we want to evaluate that at 0. So if we let this time be a 0, this whole first term is going to 0 out. Notice how our y rate of change is negative. So that means we do have a y rate of change. That means we are moving vertically in the downward direction. So we are not at rest. Tells us that number 3 is not true. And that then would tell us that 1 and 2 are answers. All right. Gave you this here. We've done a number of these in class. I would go back to that chapter, look those over. This is actually our Unit 9, Chapter 10. I put a few more here. One of them we've seen, one of them we haven't. So especially this number 3 we haven't seen yet. You can find the next one. We did do this question. But definitely this one I kind of want to go through. So let's dive into this. An object moving along the curve xy plane has a position x of t, y of t at time t, but they don't tell us what it is. They do give us dx dt and dy dt. At the time of 0, they then give us an initial position. So at the time of 2, this is our position. They want the acceleration vector and the speed at the time of 2. So letter A. All right, we don't need up there. So letter A. I'm going to get a new pen here. If you want to try that, that's something we may be able to do. However, before you really dive into this, once I get my other pen, hopefully. This was a calculator question. You absolutely want to be using your calculator for letter A when it says the acceleration vector. These are ones that we should be able to do by hand, but you're being ridiculous if you try to do them by hand. So here is your, if I wrote v of t, this is your dx dt. So if I ultimately want my acceleration vector, we could do the chain rule in here, the derivative of the inverse sine, do your chain rule, the derivative of the inside, but I'm guessing most of us have to look up the derivative of the inverse sine anyway. We don't necessarily have that one memorized. It's not one that we do often. So what we want to do, this is a calculator question. This is absolutely them testing you on your ability to use your calculator and understand that Math 8 key. So when we go to do this one, let me try to jump to the calculator. We want the derivative of this at the time of, let me just make sure, of 2. So this is our whole Math 8. We're going to find the derivative of this function here. So we're going to do the inverse sine, 1 minus 2e, so 1 minus 2 e to the negative t. Looks like I'm on polar right now. That's okay. Close that. Let me just make sure I have this correct. Yeah, and then we want to evaluate that at the time of 2. Come on, what? Let me just get out of polar. My guess is my domain is wrong, and we're going to encounter that a lot. So let's go back. Second entry. See, this is why I did this. I should have paused you guys again. Inverse sine. One minus 2e to the negative t. You probably have this answer already if you have your calculator handy. Negative t. All right, let me take one more peek. So we want the derivative inverse sine 1 minus 2e to, and then that should give it to us. All right, so we get what? 0.396. And then now do the same thing with this one, 4t over 1 plus t cubed. Yeah. Enter negative 0.741. All right, so that's our acceleration vector, and then we want the speed at the time of 2. Speed is the magnitude of our velocity vector at the time of 2. I'm going to pause you and plug this in, so you don't have to watch me fumbling around with all of this. But that should be then this big square root of these guys evaluated at 2. So you're just taking this, evaluating it at a 2. And then squaring that. Again, pretty ugly stuff here. If we let this be a 2, let me just write that as an 8 over 9. It'll be a little bit easier. All right, give me a minute. I'm going to pause you so I don't take 10 minutes. All right. So put that in there. That should give you 1.208. And now my word's frozen. It's great. There we go. All right. So throw that in. Make sure we can do that. It's a little messy. Now I look at this. I didn't square my 8/9 on the paper, but that definitely needs to get squared. All right, and then that's that. All right, letter B. We just did this recently, at least in the context of when our class compared to when we just did when I'm making this video. The idea of a vertical tangent line. We can do that with parametrics. We can do that with implicit differentiation. We just did it recently with polar, but it's the whole idea. If I have a vertical tangent, so for letter B, tangent lines, we've always talked about the slope of that tangent line. So if we have parametrically defined functions and I have a vertical tangent, then the whole dy dx equaling dx dt dy dt, dividing those, we end up with that dx dt on the bottom. The reason we would have a vertical tangent is because this dx dt would have to be equal to a 0. So if you notice, we already have what the dx dt is. If you look up here at the top, we know what dx dt is. So we're really just taking that, trying to differentiate these, inverse sine function, the inverse sine 1 minus 2e to a negative t, we want to know when that equals 0. Now, you have your calculator in your hand, so you can definitely graph this and then find that 0. That's what I would do. This is one that if you want to attack this, do the sine of both sides. So we could go through with just take the sine of both sides. So it cancels this out, and then the sine of 0 would give you a 0. Then it's a reasonable equation to solve. So if I did minus 2e to the negative t, actually let's add that over. So we get 2e to the negative t, we can divide. Take that natural log of both sides. And notice how we get a negative natural log of 1/2. So we could have done that without our calculator. But with the calculator in your hand, definitely just take this, graph it, and then find your zero. So look and see, where does it cross the x-axis, do the second calc zero, and what you should get is that negative and then the natural log of 1/2. Okay, or natural log of 2. Let me pause real quick. Okay, and that should be what, 0.69 if you graph that on the calculator. 0.693, I think it was. If you graph it, then you're going to give the decimal value, but since the calculator question, totally acceptable. All right, C, let M denote the slope of the line tangent. Write an expression for M of t, which is again the slope of the tangent line, as t goes to infinity. So, also kind of what we're now doing, or we just quizzed on this in class, relative to when I'm making this video. The whole limit as n goes to infinity. In this case, it's just the time. So take your slope. So again, this is your slope. So dy dt is that fraction. What was that? 4t over 1 plus t cubed. And then divide that by the inverse sine of 1 minus 2. And then for the sake of us being able to see this good, instead of writing this as 2e to the negative t, I'm going to write this as 2, and then I'm going to put the e to the t in the denominator and make that exponent positive, just so it's a little clearer. Well, this is m of t. This is the slope, dy dt divided by dx dt. And that's what they told you m of t is. And then they want us to find the slope, or the limit of this, as our time. Put this over here, the limit of this as our time goes to infinity. So all that's really now asking is, what is the limit of that function as we go to infinity? So I would definitely say we want to clean this up. So this would just be a 4t divided by the 1 plus t cubed times the inverse sine of 1 minus 2 over e to the t. And then now think this through. We've had to do this a lot recently. Find the limit of that as our t's go to infinity. So as you do that, if you can, again, pause me, see if you can come up with this. But the reason I had you write it like this is, wouldn't this go to 0? Because our faster growing function is on the bottom. So that would make this whole thing turn to a 1, ultimately. And then we could do the inverse sine of 1. So that is pi over 2. So while that all becomes a pi over 2, so this basically becomes a constant. If we look at what remains, if this is just going to become a number, then we really can kind of focus on here. And what you're going to see then is the faster growing function, that t cubed compared to the t, is in the denominator. So then what that would have to tell us is, overall, our limit is a 0. All right, and then the last one. So this one, when they took this question, even letter D, when they came back, I had to kind of think long and hard about this one. And this is not uncommon. The D's sometimes are a little trickier. So it says the graph of the curve has a horizontal asymptote at y equals c. So some connections here, thought process we want to kind of jump to. If I have a horizontal asymptote, remember how we found those? If you watch some of the previous videos, you would have talked about this recently, is you take your function, whatever that is, and we find our limit as x goes to infinity or negative infinity. So further, as far left as you can go and as far right as you go, if we have a horizontal asymptote, we should basically finding our asymptotes as we move further right and further left. So that's what this is saying. Limit as x either goes to positive or negative infinity for that function. So it says write, but do not solve. Right, but do not evaluate an expression involving an improper integral. So then that's another idea. Remember the whole infinity for our limits that we could use to figure out what that value is. So here's what this is getting at. There's one thing we haven't used yet in this problem, and that's this information here. They deliberately do not give you information that you're not going to use. So they gave us that for a reason, and it's for letter D. So at the time of 2, let me remember this, so 2 and then 6, -3. So they also tell us that at the time of 2, we are at a position of 6, -3. So now let's combine these ideas. Really, the 6 doesn't apply to this question in terms of letter D. What we are told is at the time of 2, our current y position is a -3. All right. And then what they're asking us to do is, well, what happens if our time is infinity? What if our time continues to grow? What would be our new y position? So it's a variation of a type of question we've done many times. But what they're good at is, again, just tweaking little things here and seeing if you can apply and make some connections between some different topics. So this we've done before, where I would have talked about, let's find our initial position and then add the change in position. All right. While our initial position is a -3, if I want to find the change in position, I would need, and this is our vertical position, right? So I would need to integrate y primed of t over the interval of 2, since that's what this position's time is, through infinity. You could actually leave this because y prime is defined. Y prime would be, was it that guy? Let me check here. Yeah, it had to be, right? Yeah, that 4t plus 1t squared. And that then should give you what our new y position was. Let me see how this is asking. Yeah, it's just an expression, so we don't need an equation. That would be all that we would need. So take the original y position at the time of 2. So that's where we're at time of 2. Let's find the amount of change. We would do that by integrating y prime from 2 through infinity. So that's tricky stuff, right? Not easy stuff. But that would be that answer. All right, when we go to the next one, I'm probably not going to go through this. You've seen enough videos. We have done this exact question. So if you were to go back to our packet, so you should hopefully have all of those packets. And if you were to, it's what, packet number 9, when we do all the polar and parametric stuff, you're going to find this question there. So you can kind of work through that, see what we did. The biggest thing, maybe I will do one quick refresh. I do that a lot when I tell you that we're done, and then we go ahead and figure it out, is just this letter A. Just because it's so commonplace, A and D being the big ones in this one. I think here, pretty straightforward. B is straightforward. C is very straightforward in terms of what you're supposed to do. It's really A and D. I'd really like you to kind of go back and remember how to do these. This is the same thing we would have just did in that previous question. And we did a few of these by hand when we didn't have our calculator, where at the time of 2, we have an x position of 1. And then they're asking you to find at the time of 4, what is our new x position? So like we just did, what we need to do is take the initial position, our initial x position, and then add the change in our x position. So the initial at the time of 2 here, our initial x position was 1. And then we need to add that to the change in our x position. So we're going to integrate x primed over the interval of 2 to 4. So what we need to recognize here, what we talked about with this, we don't know the antiderivative of this. All right, we can't say the antiderivative of this is sine of t squared divided by 2t. It doesn't work like that. We can only divide by that if it's like 2t, we divide by the coefficient. So this, you just throw in your calculator right now, you do your math 9 key, whatever that gives you is going to be your answer. So no, if you're on the non-calculator part, then you're going to be able to do the antiderivative without it. If you're on the calculator part of the test, then you're probably not, and they're really asking you to see and test you on your ability to know that we can do this with our math 9 option on the calculator. All right. All right, with that, we're, I think, over an hour if I were to stop this and look at it, and I try to keep these at about an hour to keep you from becoming too bored. So go back, you can find this answer. If you have any questions on any of these, please pop into an intervention period at some point. Let me know. And that's it. Okay, we'll see you guys.